In this video, we're going to be talking about Simon's algorithm, and this is going to be the first example of an exponential speedup using a quantum computer. So in the previous examples, we had Deutsch's problem, which was a constant speedup from 2 calls of the oracle to just 1. And in the following video, the Bernstein and Vazirani case, we were able to do a little bit better. We brought down the runtime from O of n to just O of 1, so it was a linear speedup. And here, we're going to see that in the quantum case, we can do exponentially better. So this is one of the algorithms that drew a lot of attention to quantum computing in its early stages, and we're going to talk about it now. So firstly, we can see that we have some oracle functions. So again, we're working with this oracle model of computation, where we're mapping bit strings of length n to bit strings of length n. So there's some group structure here. There's this underlying group of the integers modulo 2 to the n, and the promise here is that 2 inputs are only going to return the same value with respect to this function if one of the inputs is the other XORed with this value s. And the goal here is to find s. It's to find this hidden bit string. So we want to find a specific element of this group such that XORing it with any other element of the group results in a constant function evaluation. So it doesn't actually change its function evaluation. And the reason I mention this is because the Simon's problem is just one example of a deeper and more general problem where quantum computers have been shown to be able to do better. And that's something called the hidden subgroup problem. And we're going to be talking about it and addressing it more directly in following videos. But I just wanted to mention that and get it out of the way. So what is this actually saying? Well, it's telling us that our function is periodic, so the function values are going to repeat, and that's determined by this hidden bit string s. And in particular, this makes the function 2 to 1. So for every input, there's one other and only one other binary input that's going to return the same value. And let's just verify that that's the case right now. So we have x, and we're promised that x XORed with s is going to return the same value. So now just to verify, let's just take this as our input now and see what we get when we XOR it again with s. And of course, this just goes to 0, and we get back x. So indeed, there's only there's only a pair that's going to return the same value, not 3 or 4, and so on. So classically, how do we go about doing this? And let's take a look at the actual runtime of a classical algorithm. So it turns out you can't do much better in the classical case than just simply guessing and checking. So what that entails is you call your oracle, and remember, the goal here is we want to find s in minimum number of calls to this oracle as possible. And in the classical case, what you do is let's just say you choose some input, x naught, and then you evaluate f of x. So you make one call to the oracle, and then you just keep trying inputs, and you repeat this process, and you store your previous values and their inputs, and so on, until eventually you find a pair. Let's say xn and xm, such that xn is equal to f of xm, and then you just use the promise here that this means xn must be equal to xm XORed with s. So you can just take xm XORed with s and XOR it with xm. And remember, this is just xn. So if you have these 2 inputs, you can just do this. And of course, this here is going to just give you s. So this is how you'd find it in the classical case. But in the worst case, since there's only there's only one other input for each input out of the 2 to the n basis states. So we have 2 to the n basis states, and each input has only one other that's going to return the same value, and you need at least one of those pairs to determine s. In the worst case scenario, it's going to require 2 to the n over 2, which is just 2 to the n minus 1 calls to the oracle. And you can show that if you do some sort of randomization, that the expected time is going to be a little bit less than this, but regardless, it goes like O of 2 to the n, and this is exponential. So we want to do better than that. Exponential is no good. in computer science. So let's see what happens in the quantum case now. So in the quantum case, things look pretty familiar. We again start out with this Hadamard. We prepare our input register all in the state 0, and then we apply this n-fold Hadamard, and this is going to give us an equally weighted superposition of our 2 to the n basis states. And then I'm just going to put the output register here. And notice that the output register, all these qubits are not, we're not putting them in a superposition or anything. So that's different from the previous algorithms where we prepared it specifically in the minus state to get that interference effect. But here we're not doing that. We're just taking it to be in the 0 state. Okay, so now we apply U of f. So let's go ahead and do that. And this is pretty easy to see what is going to happen. We're just going to append the function value for each particular term in the superposition. And now we do something a little bit different. And we actually haven't done this before in any of the previous videos or talked about this type of computation, but we make a measurement and we do it somewhat prematurely. So we do it before we actually close off the interference. And this is a good example that shows the power of quantum measurement, because usually it's thought of as this sort of destructive thing, and it is, because it collapses our state vector. But in this case, it's going to collapse it to something particularly useful to us, given that this function is periodic. So let's see how that works. So now we choose to make a measurement just on the output register. So we don't care about the input register right now. We're just looking at the output register. So what happens when we measure f of x? Well, when we measure f of x, it has to collapse to one of its possible values. And it can take on 2 to the n minus 1 values, right? Because there's 2 to the n, because for each input out of the 2 to the n, there's one other that returns the same value. So there's 2 to the n over 2 unique function values. So this is going to give us, in the output register, we're going to get some function value at some x naught, which we don't know what it is for now, but now we know what x naught evaluates to. Okay, so then what's going to be left of our input register? What's going to happen to our input register after we make this measurement? Because it has to collapse somehow. It can no longer be in all these states. It has to be in the states corresponding to f of x naught. And remember, this is a periodic function, so there's more than one state. So we still have a superposition. And the superposition that we have is 1 over the square root of 2 x naught, and then we also have x naught XORed with s, because these are the two possible values that could have given us f of x naught. And that right there is the initial trick with quantum measurement that makes it so powerful, because just like that, we've encoded this information about s into our input register. But we're not done yet, because a measurement here wouldn't actually tell us anything about s. So we want to do a little bit more. And the final thing we do is we apply again a Hadamard to our input register to close off the interference. So let's trace through what happens from there. And now we can just disregard the output register. All the information we need is right here. So we're going to have 1 over the square root of 2. And then for each of these terms, the action of the Hadamard is going to be from y is equal to 0 to 2 to the n minus 1. And then we have this -1 xo or x naught, and then this scalar product with y. And this is for this term. But then we also have the same phase factor for the other term. So now we've brought up this, let me rewrite this. So we brought up the information about s into the phase factors, and this is going to be, it's going to be good for us. So this is our resulting state, and let me just rewrite this, and I'm just going to ignore these normalization constants now. So we have our sum over y, and I'm going to pull out, or firstly I'll rewrite this here. And remember, this corresponds to some input. So rewriting this, we have x naught inner product with y XORed with s inner product with y. And now we can actually just pull out this -1 to the power of this inner product between x0 and y. And our result is this superposition where we have 1 plus -1 and then s dot y. So let's think a little bit now. What happens if we make a measurement here? What are the possible cases? So if s dot y is equal to 1, then this thing here is going to become -1, and this amplitude is actually just going to vanish. We're going to have 1 minus 1 in front of that particular y value, and this is going to be 0 amplitude for that particular y. So we actually will never measure any y that's going to have an inner product with s equal to 1. So a measurement here is going to give us with 100% certainty some y, let's call it y naught, such that s dot y naught is equal to 0. Okay, so now we actually have some information about s if we make a measurement here, because we know this with 100% certainty, because otherwise the amplitude vanishes. And if this thing here is equal to 0, then this just becomes 1, and we get an actual positive amplitude here, or an amplitude that's non-zero. So all the things that we could possibly measure in the input register is going to have this property. The fact that s, our hidden bit string, inner product with that measured value is equal to 0. But it's actually not enough to determine s. It turns out we need at least n different y values such that this is the case. So let's start with y naught equal to 0, and y1, and so on until n minus 1 is equal to 0. And not only that, but these y values need to be linearly independent. Otherwise, we don't gain any new information. Because as you can see here, we have a linear system of equations modulo 2 corresponding to s. So we can actually solve this efficiently on a classical computer once we've obtained this information. But we could have only obtained it through this quantum algorithm. And you can show that it's actually very likely that you're going to find n linearly independent y values such that you can determine your value of s, and you can do it in time that's polynomial in n. So our runtime is something like Pn, where p is just some polynomial. So just like that, we've gone down from 2 to the n to a polynomial function in n, and that's an exponential speedup. And you might be concerned with how you actually determine s here, but it can be shown that you can do it very quickly on a classical computer, because these systems of equations are pretty easy to solve, given that they're modulo 2. Normal systems of equations are not always easy, but this in particular is there are fast ways to do this. So I hope all that made sense. This is Simon's algorithm. It's very interesting. And in the following videos, we're going to introduce more formally the Fourier transform, which actually the Hadamard is an example of, but we'll establish a deeper connection between that and the future videos. And then finally, we'll build up to Shor's factoring and Shor's discrete logarithm problems, which are probably the two most important problems that have been shown to have exponential speedups in quantum computing. So thank you.